Good afternoon, friends. Our today's session is on two-phase method and BGAM method. Here you will see constraints will be these two, greater than or equal to signs. This is our problem. Here objective function is z mean equal to 15 by 2x1 minus 3x2, and these are the constraints for this particular objective. Solution: convert the objective function into the maximization form. Wherever you are looking objective function like this means minimization case, that case you have to convert it into maximization in three cases, in three methods: simplex method, BGAM method, or two-phase method. In these methods you have to convert like this. After that, procedure is same for each and every method. Maximize z dash equal to minus 15 by 2x1 plus 3x2. This is converted into maximization form, that is objective function, and these are the constraints. Constraints here are greater than or equal to. Here constraints are same, subject to the constraints. Here we can add slack variable and artificial variables where to be added. Here our constraint is greater than or equal to. Here we have to add minus s1 plus a1. Wherever you are looking greater than or equal to sign, there you have to add minus slack plus artificial variable. Similarly for second equation, because here also we are looking greater than or equal to constraint. Same thing is done for this, and these are the constraints according to these two equations. Phase 1. Here we will find out initial basic feasible solutions. Here first step is assign a cost -1 to each artificial variable and cost 0 to all other variables in the objective function. Here one thing is mentioned: maximize z equal to minus a1 minus a2. Artificial variable signs will be minus in objective function. We are talking about objective function, and these are the constraints. Here initial solutions are a1 equal to 3 and a2 equal to 3, z star equal to 0 by putting x1, x2, x3 equal to 0. Similarly, we will solve these conditions are useful during two-phase method. First one is z star is less than 0 and at least one artificial variable appear in the optimum basis at a positive level. In this case, given problem does not have any feasible solution. That is first condition in maximization case. Maximize z star equal to 0. At least one artificial variable appear in the optimum basis at a 0 level. In this case, proceed to second phase. Here no need to proceed for second phase. If your case is like this, maximum z star equal to 0, then we will go for phase second. Max z star equal to 0. No artificial variable appear in the optimum basis. In this case also proceed to second phase. But in this case no need to proceed for second phase. Here we will stop our final solution if your condition is like this. This is our tabular form based on our above equations. Here we have used standard equations. These are the standard equations or in standard form which are required. This is the tabular form we have mentioned here. Here our objective functions coefficients are 0 in initial phase, that is phase 1. No need to use original coefficients. Same thing we have mentioned here according to this. Here our objective function, here x1, x2, x3 coefficients are 0. We have written same thing. Next a1, a2, here a1 and a2 plus and s1, s2 minus sign. Same thing we have written here. These are the coefficients of these variables. Here we will calculate these elements. Here minus 3 into minus 1, addition is minus 4. Here minus 1 into minus plus, here minus 1 plus 1, here value is 2. Like this we will calculate this row, and after that we will select entering variable column. Entering variable column is this one because most negative is this element. This is our entering variable column. And out of these two ratio, which is list 1 is 1. Here we will select this A1 is living variable. I have written same thing. Second step, we will do calculations by using last formula, that is equal to old element minus intersectional element into current element of the replace row. According to that formula, we will calculate these elements. And next step is, again we will select here most negative is this one, entering variable column is this one, and leaving variable is this one, because only one ratio is there. This is negative. Here our solution is this one. Here artificial variable is not there. Here I have written one sentence. As there is no variable to be entered in this basis, this table is optimum for phase first, because Z star is 0 and artificial variable is not visible here. In this table, maximum Z star equal to 0, no artificial variable appears in the optimum basis. Therefore, we can proceed to the phase second. This is our phase second. The artificial variable which are not basic at the end of phase first are removed from the table. Simplex method is applied to the modified simplex table obtained at the phase first. After this, or in this table, we will use simplex method procedure. Here we will use original objective function coefficients, and these are the elements we will copy as it is from this table. These are the elements and these are the same variables which are appear here. Same elements we have copied in this table. Only this is changed. Only original objective function coefficients we have used. Next step, we will do calculations, similar calculations. Here most negative is this one. Here living variable is here. I have written again this table is not feasible as basic variable x1 has a non-zero coefficient in Z row. So make table feasible. How to make that table feasible? Here we will do calculations. We will do calculations for this and we will find out list 1. Here most negative is not visible. Then our optimum solution is this one. This is our optimum solution. Here our objective function Z dash equal to minus 75 by 8. That is our maximization Z max, and Z mean is Z equal to 75 by 8. This is our minimum value. Minimum value. This is our Z equal to 75 by 8. That is maximum value and this is minimum value according to our objective functions. Initial objective function was minimization and converted objective function was maximization. Problem 2. This case is minimization. Here we can convert it into standard form. Same thing, same, each and everything is same. Here we will make this feasible. We will select here most negative, entering variable and leaving variable. Here I have written sentence of procedure. Similarly for this, the given problem is having non-feasible solution because here negative value is not there. Here I have written as there is no variable to be entered in the basis, therefore phase first ends here because this condition is there. Problem 3rd, minimization case. This is our problem. Phase 1, artificial variable A1, A2, surplus variables S1, S2 will be added in these equations. Similarly, we will mention or include the coefficients of these variables in tabular form. Same thing. Here we will do calculations for this. Here we will select most negative is minus 7. This is our entering variable column and least one is this one. This is our leaving variable row. Means A1 is leaving and X1 is entering instead of this A1. Then next, most negative. We will do calculations by using that formula, these elements. And after that, X2 is the entering variable because most negative is minus 5 by 3 and A2 is the leaving variable. Where is A2? A2 is this one. And here condition is like this: as there is no variable to be entered in the basis, this table is optimum for phase first because Z star is equal to 0. it appears. And in this table z are 0, no artificial variable appears, then we will go for phase second. That is the most important condition in two-phase method. Here, two-phase method, here we will use original objective function, convert it into this form. Same thing is mentioned here. Here S1 is entering variable because most negative is this one, leaving variable is 1, that is least. And hence, this is an optimum solution because no negative value appears in Z dash pro. Here our optimum solution is this one. Degeneracy case. This is our problem. This is our standard form, modified form. Here in this table S1, S2 tie. S1 and S2 is tie for the living variable. So, and any one can be considered as a living variable. Therefore, X2 is the entering variable and S1 is the living variable because most negative is this one. Therefore, X1 is the entering variable, S2 is the living variable. Here, optimum solution is X1 equal to 0 and X2 equal to 2, Z equal to 18. It results in a degenerate basic solution. Okay, 1 0 is there in solution column. Next is Big M method. Here I have mentioned changes which are important in Big M method. Multiply the inequality constants to ensure that the right side is positive. For any greater than or equal to constant, introduce surplus or artificial variable. Next, choose a large positive m, introduce a term in the objective of term m multiplying the artificial variable. That is important in objective function. For less than constants are introduced slack variables so that all constants are equalities. That we need to convert into standard form. Solve the problem using the simplex method. Rest of the procedure is same. Only m coefficient will be there in table or in equations. Solution steps are: write the problem in canonical form or standard form, which is converted into required form. There we will see artificial variable or slack variables. Add m to the artificial variable in the objective function. Add artificial variable in the objective function if that case is minimization. Means objective function is minimization. Then we will add m plus. In case of problem, suppose maximization case is there, then we have to subtract m coefficient in objective function. Otherwise, add it. This is our objective function. Here case is Z mean. These are the constants. Here our standard form is x1 minus 2x2 plus x3 plus s1. Because here constant is less than or equal to, that's why we have added here s1. Next is greater than or equal to minus 4x1 x2. Here sign is greater than or equal to. Here we will subtract slack variable plus artificial variable. Then third equation is equal to sign. Here wherever you are looking equal to sign, there we have to add only artificial variable. No need to add slack variable. 2x1 minus x2 plus a2. It should be plus sign. Why it is a2? Because a1 is already added in second constant equation. That's why it is a2. That is added in this constant. Then our modified or updated objective function is Z mean equal to minus 3x1 plus x2 plus x3 as it is plus ma1 plus ma2. Like this we have to add. Why it is positive? Because objective function is minimization. That's why it is plus. If this case is maximization, then our objective function will be minus ma1 minus ma2. Like this we have to modify, and after that rest of the procedure is same for the optimum solution. Thank you.